In section 3.2, we're going to talk about logarithmic functions and their graphs. So really important thing to remember when we get into that is, and I'll talk about it again, logarithms are the inverse to exponential functions. So last year was probably your first year being introduced to logarithms if you're in Algebra 2. If you didn't enjoy logarithms, my hope would be that this time around, it's the second time you've seen it, so it will be kind of less jarring, and maybe you can understand a little bit more. Some people are shaking their heads now. I love logarithms. Before we get into logarithms, I do just want to go over those two compound interest formulas that we didn't get to yesterday. So I'm going to write them up here. I would recommend you put the compound interest formulas in your notes. These should look familiar. Yes, compounding your interest. Hurts, yes. Okay, so on the homework assignment, some of the problems gave you the model, and like many of the models use the natural base E. And then there were some questions, I think, of financial questions on the homework that asked you, like, if you put in this amount of money, so on and so on. So just to kind of review, the compound interest formula on the left is like your basic compound interest formula. It's got that extra variable of an n in there, and n represents the number of times that you compound things. So like if you compound quarterly, n is 4. If you compound monthly, n is 12. If you compound daily, n is 365. You remember doing that? Okay. And then PERT. Does anybody remember how many times you're compounding for PERT?
Compounding continuously.
Compounding continuously. That's why we call it the natural base, because that's what happens in nature. Like things in nature compound all the time, not on set schedules like a financial institution might do. So I always give an example in terms of like population. Like when you look at those homework problems that you did, many of the models you were given for population use the natural base. Because population doesn't compound once a year when everybody has a baby on the same day, right? That doesn't happen. Babies are born all the time, throughout the year. We all grow up. We all have more babies. Okay, I'm generalizing there. But that's the idea, right? So that is the natural base. It's when you don't run on a set schedule. You just compound all the time. So just really quickly, I have an example here. And what I want to make sure everybody does is I'm going to do the work in my calculator, and I just want to make sure that if you set up the function, set up the formula, that everybody in their calculators can then get the right answer. So this is an example where I deposit $100 into a CD. So that's my fee, that's my principal. My CD earns 2.5% annual interest, so that represents my rate. Remember, when you put rate into the formula, you cannot enter it as a percent, so you have to change it to a decimal. That 2.5 would become 0.025, so R is 0.025. Remember to change your rate to a decimal. And it says, find the amount of money in your account after 3 years, that's my time, if interest is compounded quarterly. So when we say quarterly, we know to use that first formula, and for this example, n will equal 4. Quarterly would be 4 times a year. Okay. So I'm going to plug into the formula. My principal is 100. 1 plus my rate, which is 0.025, divided by 4. Why do you have to divide your rate by 4? They're not going to give you 2.5% interest 4 times a year, because then they're really giving you 10% interest. They're going to give you a fraction of your 2.5% interest throughout the year, okay? A fourth of your 2.5% interest. And then raise that to the 4 times 3, or 12. And this would be the point where I'd say, get out your calculator, plug that in, and make sure you can get the same answer that I did. Okay, don't wait until Friday on the calculator portion of the quiz. to have that be the first time you've ever calculated compound interest on your own, and you do or don't get the right answer. Okay, so do it now so that you can check it. I get $107.76. And I'm following rounding rules. Okay, so you plug that in and make sure that you can get that same value. If you don't get that value, let me know. I'll come around and I want to look at your calculator screen and see what you typed into there. Probably the most common mistake that I see students make is, I drew this up on the board, I put parentheses around 4 times 3. Most common mistake I'll see is people who don't do 4 times 3 in their head, so they don't think of that as 12. And in their calculators, they don't include parentheses, so they raise it to the 4th, and then the whole thing gets multiplied by 3. So you come up with a much larger number. And then for continuously, we'd use that formula with the PERT, the compounding continuously. I don't need a value for n, so I'm just plugging in 100 times e raised to the 0.025 times 3 for 3 years.
You learned 3 more steps.
Yeah. And you come up with $107.79. Let us know if you don't know where your E button is. You should be typing like 100 and then a second natural log. Okay, the E should be right above natural log, so use the second function. See if you can get $107.79. And then type 100. And then you set it.
Type 1 above your natural.
So now in parentheses, everything that's in the next one are good. Everybody else okay?
I have 2 e.
Yeah, so normally there's one, like the one below, or the one that's associated with natural log will also pull up an exponent.
Yeah, and then there's one above the division sign that gives you the exponents.
Does it work? I would use the one with natural log. What's that? Oh, thank you. I think it used to be an account. Emily has alerted me to a typo. ACD. A certificate of deposit. Okay? So if you had any trouble with yesterday's homework assignment, completing any of those problems, or maybe you didn't know where your E button was for your homework assignment, now you know. Okay, you can use those things. Okay, let's start talking about logarithms. Yay, logarithms.
Well, maybe you're not
Okay. Also important to remember with this statement, not only is the logarithm really just representing an exponent, it is the inverse to the exponential function. So that's an idea that we're going to take with us when we go into graphing. How can we use its inverse properties to help us so that we can graph the logarithm? Okay, so a logarithm is an exponent. Here's the definition of a logarithmic function. This is our basic logarithmic function. We're going to be working with the basic logarithmic function when we're graphing. Okay, so the logarithmic function f with base a is f of x equals log base a of x. Underneath that equation in the quotes, that's how you say that, right? Log base a of x.
So the formula I was talking about it doesn't show up in the homework, but if you wanted to solve this with your calculator, would it be log A over log X?
Switched. Log X over log A. Yeah, we'll do that one tomorrow. That's the change of base formula. I would practice saying it like a mathematician will say. That kind of helps you reinforce that subscripted number is always the base to the exponent. Okay, the answer to the log, the f of x or the y, that's the log, that's what it is. So that number is the exponent in your exponential expression. Remember that this is the inverse of the exponential function a to the x, so some of our notes from yesterday still apply, like a must still be greater than 0. You won't ever have a logarithm whose base is a negative number. Okay, so the base to a logarithm is always a positive number. Also, a will not equal 0, or sorry, not equal 1. Will also not equal 0 because it's positive. But it won't equal 1 because we talked about yesterday an exponential function 1 to the x is really just a constant function. So that value gets excluded. You can have log bases that are greater than 1, and you can have bases for logs that are between 0 and 1. So you could have a fraction base. Okay. Also, just to kind of put this in context of the exponential function, when we say y equals log base a of x, that's only true if and only if x equals a to the y. Okay, so that's like, making a connection between how you rewrite from logarithms to exponential expressions, and that will be really helpful. Remember, the base to the log a is the base to your exponent. Okay? The number that is the exponent, that's what the log is equal to. So the number on the other side of the equal sign that is the answer to the log, that is the exponent. That's your y right there. And then that base raised to that exponent equals whatever is in the end of your log. Okay? So kind of keep that in mind if you're ever needing to rewrite from one form to the other. Here are 4 properties of logs that I will have you write down in your notebooks. And we'll talk about them in a moment. Now the first 2 properties make a lot of sense if you think about that very last statement on the previous slide, like if you rewrite them in exponential form. So when we say log base a of 1 is always equal to 0, okay, and we'll use this when we're graphing things, think about what that means as an exponential equation. So your base would be a. Remember that your exponent would be the thing that the log is equal to, so your exponent would be this number 0. And if I ever asked you, what is a to the 0, you would tell me 1. So it will always be the case, no matter what the value of the base, if you have a log that's equal to 0, okay, then you had a 1 right behind it. Okay, so the log base a of 1 will always be equal to 0. And then similarly, the next statement makes a lot of sense when you think about it in an exponential equation. So this one is saying a to the first equals a. Do you agree with this exponential equation? Yeah, anything raised to the first is itself. So a log base a of a, if the base matches what you're taking the log of, then that will always be 1. So that will always be be true. You should have seen the inverse properties last year in Algebra 2. And I think the thing to remember about the inverse properties is they're not supposed to be like a challenging property. It's actually supposed to simplify really nicely and easy because they're inverses. And inverses undo each other. So if I look at this first example, if I write out some kind of expression without these a's in it, I could say something like this. Suppose I come across something that looks like log base 8 of 8 to the 5th. Okay. Then when I see that my logarithm base is the same as the base for an exponential expression I'm taking the log of, then those things are going to cancel out, and that whole expression is just equal to 5, the exponent. Okay. That should make sense if you thought about that in its exponential equation, right? It would be 8 to the 5th equals that thing that you're taking the log of, 8 to the 5th. Yeah, that checks out. So that makes sense. Okay. And then likewise, if you had something like, let's say 7 log base 7 of 2. What you're noticing is the base to your exponent matches the base to your logarithm in your exponent, so those things are going to cancel out, and that whole thing is just equal to 2. That's the inverse property. They would undo each other, okay, and so they cancel each other out. And then the last one I would hope you're okay with after our discussion on one-to-one property yesterday for exponential functions. If you have the same base for logarithm, then x and y have to be equal, the thing that you're taking the log of. Okay, so let's talk about what changes for graphing. Okay. Yesterday, when you graphed your exponential functions, you should have noticed some similarities in the domains, the ranges, the horizontal asymptotes, the y-intercepts, the increasing and decreasing sections. And so we're going to see some of the same things for logarithms. So we're going to look at what if we were graphing f of x equals log base a of x when when a is greater than 1. Okay, what things will be true? Well, one thing I'll say is remember that the log is the inverse to the exponential equation. And if we go all the way back to chapter 1, when you're finding inverses, whether that be in a table of values, on a coordinate plane, in an equation, the main thing about the inverse is that you switch x and y, right? So when we switch x and y, we also switch things like domain and range. So yesterday, our domain for exponential functions was always what values? Domain yesterday. All real numbers. That's now going to be our range. We're switching x and y. So all the x's from yesterday that were our all real numbers are now part of our y's for our range. And then yesterday, you should have noticed for your range was always restricted by your horizontal asymptote, right? In a very basic function that was 0 to infinity. Okay? Now that becomes our domain. So your domain for a very basic logarithm graph is always going to be 0 to infinity. Okay? You can test this by using your common log button on your calculator or your natural log button on your calculator and try doing a log of a negative number. Like do log of -3 and it will say domain error. You can't take logarithms on negative numbers. Okay. And then yesterday we would have identified a horizontal asymptote, a y equals, but remember we're switching x and y, so that now becomes x equals a number and is a vertical asymptote. So your vertical asymptote will always be at x equals 0. Your y-intercept used to be at 0, 1. Now you have an x-intercept at 1, 0. And if your a value is greater than 1, you will be increasing for the entire domain from 0 to infinity. And you won't have any decreasing. Okay, you're increasing for all the values that work in the function. Now, those things could change with shifts or reflections. Okay, so especially like domain, vertical asymptote, x-intercepts, those things change with shifts. Increasing and decreasing, these things can change with reflections. Now, the last thing that's up on that screen is a table of values. And what I would do is think about yesterday, we did all the x's, -1, 0, 1, and then we would plug in to find our y. Well, we're switching x and y now, so those values, -1, 0, 1, become my y's, but we can't take any negative numbers for our logs, so we're going to take off the -1, and then we can use our two properties of logarithms from the previous slide. X, if we do log base a of 1, it will equal 0, so that's that first property. If we do the log base a of a, it will equal 1. So for finding ordered pairs on your graph, and I'll show you this when we actually have a number, you'll always have the ordered pairs for a basic logarithm graph, 1, 0, and a1. Those will always be on a logarithm graph. So let's put this to use so we can see how this works. Yesterday I think we did the log base 2 of x, 2 to the x. Today we're going to do its inverse, f of x equals log base 2 of x. Okay, so what I recommend doing is going back to the basic function. Log base 2 of x is a basic function because there's no other numbers besides the base and then what we're taking the log of. And we're going to say, we're going to put those y values or those f of x values equal to 0 and equal to 1. So what we're looking at is really saying, what is x when the log base 2 of the number is equal to 0? And if you look back at your properties of logs, then x is always 1. So like I said, you're always going to have, for the basic log function, the ordered pair 1, 0. If you put 1 in for the other y, then you're saying, what is x so that the log base 2 of x is equal to 1? Then x must have been 2, if you look back at your property of logarithms. So this is the ordered pair 1, 0, and this is the ordered pair a1, where my base is now a, so 2, 1. Okay, and that will change with whatever base you're working on, but you're guaranteed those 2 points at the basic log function. I can then do domain, range, vertical asymptote, all of those things. Because there's no shifting in this graph, this is a basic logarithm graph, my domain is going to be from 0 to infinity. My range is going to be from negative infinity to positive infinity. My vertical asymptote is going to be x equals 0. So that would be helpful on my graph for me to draw. And my x-intercept, we have no shifting, so it is that 1, 0. I'll go 1 to the right and 0 up or down, so I'll be on the x-axis. And then this one has no shifting or reflecting, so I'm increasing over the whole graph, and there is no decreasing section. Okay, so I can answer those questions. Now I'll use those, mainly I use the points and the asymptotes to help me graph. So I have 2 ordered pairs, 1, 0, and 2, 1.
Since you found a vertical asymptote at x equals 0 and increasing, shouldn't it be 0?
Oh, yes. Yes, thank you. I'll change that. It's increasing for the length of the domain, 0 to infinity. Thank you. Okay. And I'll draw in my vertical asymptote there at x equals 0. Now, this is the first logarithm graph that you've done, so if you wanted to, you could find more points that worked. Okay, so if you're like, oh, I'm not really sure what those 2 points are doing, okay, I could find more points that work, and you kind of have to pick carefully what you want them to be equal to. So, like, I might choose an x that is 4, because I can easily evaluate log base 2 of 4. What exponent for 2 gives me 4? 2. So you have the order pair 4, 2 on your graph. Then you could do another one, like another good one would be 8. What exponent of 2 gives us 8? 3. So we would have 8, 3 if you want another one. So this side is slowly increasing, where this side comes down to that vertical asymptote, and it's going towards negative infinity very fast on the left side of the asymptote. Notice that this shape is similar to that of the exponential function, right? And it should be, because it's the inverse function. Remember the idea that when we switch x and y for the graph, we're reflecting it over the line y equals x. Okay? So think about if you were to graph that exponential function like this. Those two graphs are getting reflected over the line y equals x. And that is true. Any questions on graphing the logarithmic function? Let me show you one example with a shift so that you kind of get used to what that would look like. And this is that one where I'm saying, because this is going to be on the no calculator section of the quiz on Friday and the no calculator section of the test next Thursday, it's going to be really important that you kind of go with the shifting method, only because logs aren't always easy to evaluate. So like on that previous slide, if I had picked, like tried to evaluate the log base 2 of 6, I don't know what exponent of 2 gives me 6. I can estimate it, but I don't have an exact value. So by using this method of shifting the graph, the basic log graph, then you're better able to find points, and it won't eat up as much of your time finding the points. So notice that even though this says log base 2 of x minus 3, in my table, I have just log base 2 of x. I'm only going to do the basic log function, which should be really easy. When I put in 0, x would be 1. When I get out 1 for the log, then my x is the base, which is 2. And I'll just take those 2 points, which are easy to evaluate every time, and then I'll just shift them. If it says x minus 3 in parentheses, what direction are we going? Right. If that minus 3 was outside of parentheses, or there were no parentheses, then we would be going down 3. So we're just going to take those 2 points and shift them right 3. So on my graph, I would start with 1, 0, and 2, 1. And I'll make those small. But I just need to take those points and shift them. So right 3, right 3. What else will shift to the right 3? Besides my points. My vertical asymptote will also shift. It would normally have been at x equals 0. Now it's at x equals 3. Which that's helpful to draw, so I know to go towards my asymptote on the left, and then I'll slowly increase on the right. Okay. And so the whole graph just got shifted right 3. Now I can answer some of those other questions as well. Domain is going to be related to your, oops, I put that in the wrong spot, sorry. Domain is going to be related to your vertical asymptote. So now my domain, instead of 0 to infinity, is 3 to infinity. my range is all real numbers. My x-intercept on this one works out pretty nicely, okay, because I just took that graph and moved it left, or sorry, moved it right 3, so now it's at 4, 0. And then I'm increasing from 3 to infinity with no decreasing. Are you okay with this? Okay. Now, if you shifted and you shifted like up or down, finding your x-intercept might entail a little bit more work. So like if you shifted up or down, then what I would recommend doing is our old method that works for any function, plugging 0 in for y, and then solving backwards for your x-intercept. Just like we did in that question someone asked on the homework, where we put 0 in for x to find the y-intercept, and it was 3 and 1/64. Okay, we would do that same thing here with the logarithm if we did some shifting there. Okay. Any questions on that? Now, I won't do this example, but I just want to talk about really quickly a question of graphing that could be on the calculator portion would be a natural log graph. So natural log is the log with base e. Okay. This one I really don't have to have a calculator for. I know that when my f of x value is 0, my x value is 1, and when my f of x value in this graph is 1, then it is whatever the base was, and the base was e. So I would know to go 2.718. Okay. And I could graph that 1, 0, and then 2.718, 1. And I'll have that graph, and you could answer all those questions. It'll be very similar. If they're shifting with natural log, then you can choose just different values for x, plug them into a table, and get decimal values. Okay. Here's your assignment and a couple other reminders about things that are happening soon.